Do you know that GPUs can multiply large matrices in the scale of thousands in just milliseconds? Let me show you exactly how that works. And we are going to solve two real-world GPU problems in LeetGPU while we are at it. So welcome back to Forward Logic. I am Christy Varghese. Today we are going to do two LeetGPU problems, matrix multiplication and matrix transpose, using CUDA on an actual NVIDIA Tesla T4. If you have been following our CUDA series, this is the moment where things get really real. We are not just going to write code, we are going head to head with GPU Judge. Stick around till the end because I will show you a subtle index trick that trips up almost everyone on the transpose problem and cost you wrong answer. So first, what is even LeetGPU? Think of it as like LeetCode but for GPU programming. Instead of solving algorithmic puzzles in Python or Java, you write CUDA kernels that run on real hardware. In this case, we are using Tesla T4, and this is the platform I am talking about. You go to your challenges list on the left, the CUDA editor on the middle. So you can see here, the CUDA editor is on the middle, and when you hit the run button, your kernel actually executes on T4. There is a leaderboard, performance benchmark, everything just like LeetCode has. So today we are tackling two easy rated problems, and I want to be really honest with you. Easy in GPU land is not same as easy in algorithm land. The math is really simple. The indexing will break your brain if you are not really careful. So I got transpose wrong on my first attempt. We will talk about that why in the future sections. Before we jump into code, a 60-second CUDA mental note. You need this, otherwise the kernel code will look really like a black magic. In CUDA, you have your CPU called the host, the GPU called the device. You write a special function called a kernel, and you decorate with hyphen underscore global underscore and launch it with a grid of blocks where each blocks contains the threads. Think of it like an apartment in the building. Grid is the city, blocks are the buildings, and threads are the people inside. When you launch a kernel, every single person wakes up at the same time and does their job in parallel. For a matrix, we use 2D grid. Every thread handles exactly one element. Thread touches only the element at 2, 3. That's the whole trick. 3 variables you need to memorize here. One is the block IDX, which block I am in, block dimension, how big is my block, and thread IDX, where I am inside my block. So the global row is like block IDX of y plus multiplied by block dimension of y plus thread IDX of y, and global column is exactly the same. Just replace the y with x. So that's it. We will use the exact formula in the both problems, and this is something that you need to pick it in your mind to do or tackle any GPU related problems. So all right, let's dive into problem 1, the matrix multiplication. We have a matrix A of dimension n cross n and matrix B of dimension n cross k. So we need to compute C A cross B, which gives us a matrix of dimension m cross k. So all the matrices here are stored in row major. That means that they are stored as 1D flat 1D arrays in memory, row by row. So basically the formula for this multiplication for each element of C is sum over A I cross K or A row I cross Bi of columns. So that's the basic logic behind finding the matrix multiplication. Then you can see the first example here. We have a 2 by 2 matrices, both are 2 by 2. When you multiply that, you get a 2 by 2 matrix C. Then if you have a 1 cross 3 or 3 cross 1 matrix, you will get a 1 cross 1 matrix. So that's simple matrix multiplication, and we'll be doing it in scales of thousands, not in hundreds. So let's check the editor part here. So basically it is giving out A, B, C, M and K. You can see that this is the whole function where it takes in or where we does the code logic. This is the kernel function which is initiated by the global part. So we take the device pointers A, B, C and the dimensions M and K. So we cannot change that. Those are the inputs. Our kernels takes in the same pointers plus the dimensions. Now what we have to find out is the threads, rows and column. So this is the logic like I explained before. The to find the row, you have to add multiply the block ID and the dimension and add the thread ID to find the row, and column in the same way just replace Y with X. And sometimes the thread ID or the thread might be out of boundary. We might need to check that. So that's the boundary check that we had to see whether the sometimes our grid might be slightly larger than our matrix. So that's why this check is required. Now we do the actual multiplication. We loop over the shared dimension n, and inside it all you have to do is to multiply each rows element with each column element in the thread. So that's really simple. So this logic is really simple in such a way that all you have to do is to skip this row and add this element to move to the next row or next element, and the exact same logic applies here, and you just add them up and copy that to an C. So that's the basic logic here. Then we have functions that defines the threads per block and block per grid. These are standard in LeetGPU, 16 by 16 threads per block, and that is like 256 threads. A common sweet spot for most modern GPUs. The grid size formula will be like K plus 15 by 16, which gives us the ceiling division trick. Here K is 17. We need only 2 blocks. So we will get integer division would give us 1. So we just add 15 before dividing to the roundup. Then we launch the kernel, wait for it to finish it up, and we are done. So while running this, you can just click the run button. After signing, all you have to do is to run and then submit this particular problem. It will be etc. I have tried it a couple of times. You will have your matrix multiplication done by this time. Yeah. Now let's switch into the second problem that we have in our mind, that is matrix transposing a matrix. Given we have an element of row by columns matrix, we need an output matrix by columns by rows. So the rows become columns and the columns become rows. That is really simple, right? But here's where I made my mistake on the first try, and I want to show you exactly what went wrong, because it will save you 20 minutes of frustration. So in the input matrix, the element at position yx has flat index y cross column plus x. After the transport, the same element should land at position xy in the output, which has the dimension columns dot rows. So its output should lie in x cross row plus y. Notice the output stride is not rows, not columns. So that that's the catch. If you write x cross columns plus y, it will become the wrong answer, because output matrix has different shape now. Just keep it in mind while you write this particular problem. So in the code editor, you can just take the logic from here. It's really simple. Like I explained below, you have to just write the logic for the sum. X is the column, Y is the row of the input matrix, and always anchor your thread coordinates in the to the input. That's the ground truth. Read the output index again. It's x cross rows plus y, not x cross columns plus y, because the shape has changed. The output matrix has rows, columns, because after transpose, the number of elements of rows are now columns, and the number of breadth becomes the length. So take a deep breath and read it again, since this makes sense later. So after doing that, only the solution is basically the simple. We have the same logic here. We just exchange the elements using the logic I have explained above. After that, rest of the problems are pretty much simple. This is like standard that we have seen in LeetGPU till now. The grid dimensions are based on the input shape. Columns are along X and rows are along Y. This stays consistent without thread to element mapping. And on LeetGPU, the device pointers are already given to you. You don't have to allocate or copy. The platform handles all of that. Compare this to raw code from our. You can write a code using cursor or anything. You can just compare how they allocate and deallocate and copy from the host to device and device from host as well. So that's the real version. This is where you try to learn how to write kernels at all. That's all. So once you have this code at your end, you just run it out. It's going to be a breeze. It will be accepted as I tried it a couple of times. So right now you were able to multiply two matrices as well as take the transpose of a matrix as well. So by end of this particular video session or this session, there is three things that I want you to walk away with today. First is 2D thread indexing formula. Row is block ID into block dimension plus thread ID. Same column is the exactly same, but instead of Y you use X. This works for almost any 2D CUDA kernel that you will ever write. So just memorize it. Second one is row measure indexing. Element at a row are column C in a matrix with W columns sits flat at index R cross W plus C. So after transpose that changes, the width changes, so your stride also changes. That's the bug everyone gets. Third, LeetGPU is genuinely a great way to practice. You get really good hardware, real benchmarks, and the problem set is growing. I will link that in the description. So drop your LeetGPU score in the comments, or if you have tried this and run it in a different bug, tell me, so I can learn from that as well. So if this was useful, subscribe. We are building towards shared memory optimization, which is where GPU programming gets genuinely magical. See you there in the next one. Bye.